Hi everybody, here's a super quick version of what we went over in today's talk. We went over the period of a pendulum, and so one of your missions last week was to play with the pendulum and pull it out by some angular measurement. I'm going to do 20 degrees here, about 20, and I'm going to let it go. And hopefully you discovered some stuff when you did this, and if you haven't, you can still do it and turn it in on Google Classroom, please do. But we found that with it set the default position of zero point 0.7 meters in length, that it took about 1.7 seconds. Right? So just to verify that, start, stop, about 1.72, start, stop, 1.7. You can see it takes about 1.7 seconds. I've actually done this probably 6 times today or 7 times today. I'm always getting right around 1.7 seconds when the length is that length. Okay, we hopefully you experimented with this, and when you made a pendulum shorter, it had a much lesser period and a much higher frequency, right? So now it's taking much less time to go back and forth. Start, stop, I don't know, like zero point 0.8 seconds or something. And if we make it longer, now it's a full meter, and the length is the length is 1 meter, and the period is about, start, it just glitched. I'm going to redo that trial. Start, stop. So notably longer than our 1.7 seconds at our default position of 0.7. Right? So the thing with the pendulum, you make it longer and it takes longer to swing, and you make it shorter and it takes less time to swing. The other main factor is, think about what's accelerating it downward. It's gravity. So if gravity plays a role, then you might suspect more gravity pulls it harder and makes it swing more quickly, and you would be correct in that. So we talked about it briefly, but we came up with this formula in class today that this is how long a pendulum takes to swing. Okay, this is how long it takes for one full cycle. This is the period of a pendulum is 2 pi times the square root of L over G. Okay, and in fact, when you go ahead and you put in these numbers, right, when you do, period of the pendulum that we're looking at is 2 pi times the square root, I'm going to draw that in, of that's a 0.7 meter pendulum, and G on Earth is about 10 meters per second faster every second. G on Earth is about 10, right? And so this is under a radical. I'm just going to draw it in by hand because it takes less time than trying to be fancy, right? And we found today that when we do this math, we get t equals 6.28 approximately times the square root of 0.07. Guess what we got? We got about 1.7 seconds. Oops, 1.7 seconds. When you do this math right here, try it out. This is a quantity. It's the square root of 0.7 divided by 10. This is the square root of 0.07. Multiply that by 6.28, and you get 1.7 for the period. So, which exactly matches what we see experimentally here when we do it. Okay, so there's the formula. No big deal. There's a couple times you have to run that formula on the new problem set 18, that is up and running on the Google Classroom right now, right? And so, but what about, so let me get rid of this example stuff here, and let me get rid of this stuff here. Pretty straightforward if you're looking for period. You just multiply 6.28 times a number that's under a radical, which is L over G. Okay, pretty straightforward. But what if I say how long is the pendulum and I give you the period? Or what if I give you the length and the period and you need to find G? So let's solve this equation. We have it solved right now for period. Let's solve it for both L and G. And so you don't run into any real algebraic problems when you go to solve your work on your problem set, right? So here it is. So the way to solve this problem for the other variables L and G is like this. Well, first thing I'm going to do is get rid of the confusing thing, which is this radical. And the way to get rid of the radical is, the square root of L over G squared is just L over G, right? But if we square this to get rid of the radical, we've got to square everything else too. So we get period squared. So let's just square everything. period squared equals 2 squared, which is 4, times pi squared. I'm just going to write it because it's easier that way. Pi squared, right? So period squared equals 4 pi squared times L over G. Let's multiply both sides by G. Right? Let's get rid of the division symbol there by multiplying both sides of the equation by G. And I get G times period squared. G times period squared. Oops, that's not a squared now, is it? G times period squared equals, I'm just going to do this. Copy and paste. All right, so I multiply both sides by G. And so if I want L alone, I divide by 4 pi squared. Okay? So, and if I want G alone, I divide by period squared. So let's just write those equations down and then put circles around them. This is the derivation, right? And now let's switch into red for our other form, for our final formula that we might find useful. Colors are here. Okay, so let's go for, I don't know, let's go for G first. It's right there. G equals what? Well, just get the t squared to the other side by dividing both sides by t squared. So G equals that quantity. I'm going to put brackets around it. That should be black, sorry. This quantity here, 4 pi squared times L, and I divide that by period squared. Okay, that's G. G equals, so when I say what is the gravity on a planet where the astronaut takes her pendulum of a known length and she times the period to be this value, whatever. Well, what's G on that mystery planet? Well, now you know how to solve it for G, how to find out, given length and period, you can find gravity. Now let's do the same thing going to this formula up here. Solve it for L. Okay, well we want L alone. Let's just divide by 4 pi squared. So let's just take this whole formula. Let's just take this whole formula, copy it, and bring it down here and say L equals, well, L equals GT squared, but it's over. We're dividing both sides by, we left L where it was. We have this formula here. We leave L where it is. We divide by 4 pi squared. Divide both sides by 4 pi squared. And so we get GT squared divided by 4 pi squared. So this is a quantity in the numerator. Gravity times period squared. It's superscripted my bracket there. Hold on. That's a quantity. And this is a quantity, 4 times pi squared. Right? So that's 4 times pi squared is also a quantity. So how long is a pendulum? Given what G is, given G and period, how long is a pendulum? Well, it's G times period squared over 4 pi squared. And so we'll put that one in red too. So basically we have three formulae you might want to be really thinking about right here. I'll just do this. We have this one here. We have these two here that I put in red. So this is the formula in all its possible iterations, right? If I say, how long does it take? If I say, what's the period? Or how long does it take? How long does it take? Or another way to say that would be, what is the period? Okay, you use that formula. And if I say, what is G on this mystery planet? What is G on this mystery planet? What is the strength of gravity on this mysterious planet? Right? What is G at a given place or on a given planet? You would use this one here, where we saw this one right here. What is G? There it is. G is 4 pi squared times L divided by t squared. Right? And if I ask you, how long is the pendulum? I think there's a question about little Johnny's new swing I just wrote. How long is little Johnny's new swing? How long is, I think I spelled it like this, Lil Johnny's new swing. And I told you that little Johnny, or how long is any pendulum, right? This is the proper way to say it. How long is any pendulum? Gravity times period squared divided by 4 times pi squared, right? So I think on this particular problem set, I said, little Johnny got a new swing and he timed it and he got the period, and I'm asking you to calculate the length. So that's all I can ask you regarding this question is how long does it take, or what is gravity at that position, or how long is the pendulum, and that's it. That's all I can ask, and that is our class in a nutshell. All right, guys. Talk to you soon. Take care. Bye.